Hello everyone, allow me to extend a warm welcome to you. My name is Zahra Shamsipour, bachelor's student of mechanical engineering from Guilan University. And what I'm going to talk about today is a finite element analysis of hip replacement stem design. My presentation is divided into three parts. I'll begin with a short introduction, then I will explain 3D modeling, and finally we have results. Let me start with some general information on total hip arthroplasty or THA. As you are all aware, the hip joint is one of the largest joints of the body, which plays an important role in bearing the body's weight. When arthritis progresses to its higher levels, arthroplasty is performed to reduce the pain and increases the joint range of the motion. THA or total hip arthroplasty is considered one of the most successful procedures developed during the last century with excellent long-term results. As you know, it's performed by implanting hip implants in the medullary canal of the femur bone. Hip implants have differences in terms of geometry and construction. Most studies have focused on detecting the mechanical behavior of the hip implant in the distribution of different forces, types of implant, mechanical design, or mechanical surface treatments during the manufacturing process. Obtaining the mechanical stress distribution patterns in hip replacement plays an important role in implant design and predicts potential problems such as implant loosening or the need for revision. So, depending on the studies that have been considered in the past, it's clear that the design of the stem is very important and effective for improving the quality of joint replacement and quality the surgery and finally the patient satisfaction. This study aims to consider the biomechanical effect of the hip implant design on the bone and implant in terms of stress distribution in three cases of daily activities: standing, sitting, and stairs up, by using the finite element method. To investigate the effect of the design of the stem on the stress distribution of the bone and the stems, three types of cementless stems available in the market were modeled on SolidWorks. The modeling was done based on the designs of the two reputable companies. These stems are different in length of set, neck shaft angle, and thickness. The measure of each parameter is shown here in these figures. As you see, stem C has the largest amount of thickness and length, then A, and then B has the least amount of thickness and length. Stem C has the largest amount of set 2, then B, and then A. About neck shaft angle or NSA, stems A and B are the same and NSA of C is less than the others. To create a 3D model of the bone, the CT scan images of the femur bone that belongs to a 30-year-old man with a height and weight equal to 170 centimeters and 86 kilograms were used. Then the model was imported into Trimmatic software, and there the bone was cut in diaphysis and epiphysis, and then each implant was placed in the medullary canal of the bone. After that, meshing was done on Trimmatic 2, and 4-node tetrahedral elements were created. After assembling the implants and the bone on Abacus software, they were utterly bound to each other by assuming complete integration between the stem and the bone. The properties of the used materials are considered to be homogeneous, elastic, and isotropic. The properties of the implant material were assumed equal to titanium. In this study, three loading conditions of standing, sitting, and stairs up were applied to the head of the models, and the values of these forces are shown here in this table. These values are corresponded to 80% of each loading cycle and belong to an 86 kilogram person. Also, the lower part of the femur bone was considered a boundary condition and was completely fixed. Now, I'd like to move on to the next part, result. I think the contours perfectly show that in the standing position, the maximum values of von Mises stress in stems are concentrated in the internal parts of the implant, in the neck and collar areas. On the other side, maximum values of von Mises stress in the femur bone in the standing position, and with all three implants were distributed along the shaft and concentrated in the diaphysis part of the bone. As you see, it's the same with a sitting and a stairs up position. Here we have two comparative graphs that show the maximum values of foam mass stress in stems and bone. According to graph A, the bone bears more value of stress in the position of stairs up, sitting, and standing, respectively. As you see, stem B produced more value of maximum stress in the bone than the others. Next, stem A, and then C. According to graph B, stems B and C bear more value of maximum stress in the position of stairs up, standing, and sitting, respectively, but about A, it's like the bone. Stairs up, sitting, and then standing. Also, in all three activities, stem B bears the most value of stress, then C, and then A. There's an exception. In sitting, the maximum value of stress in A is observed more than C. Also, to check the stress distribution along the implants, a path was drawn along the length of each implant from the beginning of the neck to the end of each stem. According to graphs, the stress distribution along implant C is more uniform than the other two implants in standing, sitting, and stairs up. In addition, implant A behaved more uniformly than implant B in all these activities. That was one of the critical indicators of choosing the correct stem, the right stem for surgery. So, this study showed that thickness is a key parameter in designing a suitable stem. As seen, if the value of thickness is less than a certain amount, a great value of stress is observed in the implant in the bone, which increases the risk of the fracture in them. On the other hand, if the thickness of the stem is more than a certain amount, it not only reduces the strength of the bone due to the reduction of bone volume during surgery, but also increases the risk of increasing the stress shielding effect and subsequently increasing the possibility of revision. Also, depending on the obtained data in this study, observed that offset changes caused changes in stress distribution and increased the risk of the stress shielding effect. It was also observed that the greater value of the length could positively affect the distribution of stress and its maximum value due to its more profound implantation in the medullary canal. It was also observed that implant C with a lower neck shaft angle compared to the other models behaved more uniformly in stress distribution along the stem. Therefore, it can be concluded that a smaller angle leads to a more uniform stress distribution along the stem. However, the patient's physical properties such as the bone size, gender, and age can determine the value of these parameters. Therefore, it's imperative to plan before surgery to check and choose the right implant according to the patient's physical properties, because choosing an implant with the correct dimensions for the patient is very effective in the treatment package, and it reduces the possibility of resurgery and revision. Well, finished. That's it from me. Actually, this study was my last bachelor's project, and I really hope you like it. Please don't forget to like and subscribe. At last, I want to thank you for your attention. Goodbye!